Welcome to G Fun Facts Online. Today, we are stripping away the noise of the macroscopic world to enter the absolute silence of a high vacuum chamber at King's College London. In this chamber, something impossible has happened. A team of physicists has taken a speck of glass, a microsphere just 5 micrometers wide, roughly 1/20th the width of a human hair, and subjected it to an environment hotter than the center of the sun. Specifically, 13 million degrees Celsius. Yet, the glass did not melt. It did not vaporize. It remained a solid, perfect sphere. Today, we are going to deconstruct exactly how this paradox exists, what it teaches us about the fundamental laws of thermodynamics, and why this tiny glass bead might just be the key to understanding everything from the molecular motors in your cells to the nature of quantum gravity. Let's dive straight into the physics of the impossible. To understand this experiment, conducted by Dr. James Millen and his team, we have to dismantle your intuitive understanding of the word heat. In our everyday lives, temperature is a measurement of internal vibration. If you put a glass marble in a furnace, the atoms of silicon and oxygen inside that marble start vibrating violently. They shake until the chemical bonds break, and the solid becomes a liquid. That is internal temperature. But in the field of levitated optomechanics, there is a second kind of temperature, the center of mass temperature. Imagine that glass sphere again. But this time, imagine it is floating in a perfect vacuum. Inside the sphere, the atoms are calm. They are sitting at a comfortable room temperature, about 20 degrees Celsius. However, the sphere itself, the entire object, is moving. It is thrashing back and forth, vibrating and jittering with incredible speed and randomness. If you were to measure the kinetic energy of that whole sphere moving around and equate it to the energy of a gas molecule, the temperature required to create that much motion would be 13 million degrees. This is the breakthrough. The researchers created a system where the internal temperature and the center of mass temperature are completely decoupled. The sphere is effectively living a double life, internally cool, but externally experiencing an inferno of motion. How do you achieve this without touching the object? You cannot use mechanical clamps, and even air molecules would be too disruptive. The team used a device called a Paul trap. You might be familiar with optical tweezers, which use lasers to hold particles, but lasers heat things up. A Paul trap uses oscillating electric fields. It is the same technology used in mass spectrometers and trapped ion quantum computers. These electric fields create a deep potential well, a sort of invisible cage that confines the charged glass sphere. Once the sphere was trapped in this vacuum, a vacuum so deep that air molecules were virtually non-existent, the team introduced the chaos. They injected a noisy voltage signal into the trap. Think of this as giving the sphere a series of random, violent electrical kicks. Because there was no air friction to slow it down, the sphere retained every bit of that kinetic energy. It started moving as if it were being bombarded by gas molecules in a stellar core. Dr. Millen described it perfectly, stating that the object moves as if you had placed it into a gas that was 13 million degrees hot. But because it is in a vacuum, there is no gas to transfer that heat to the atoms inside the glass. It is a kinetic inferno isolated in a void. Now this is where the story shifts from a cool party trick to serious physics. The team didn't just heat a particle, they built a microscopic heat engine. A heat engine is simply a device that turns thermal energy into mechanical work. Your car engine is a heat engine. It takes the heat from exploding fuel and turns it into piston motion. In this experiment, the hot source was that chaotic electrical noise driving the particle. The cold sink was the cooling feedback loop of the trap itself. By cycling the particle between these states, essentially expanding and compressing the trap like a piston, they created a functioning engine at the microscale. This is where we run into the weirdness of microscale thermodynamics. In a standard engine, like in your car, you are dealing with trillions upon trillions of atoms. The laws of thermodynamics work on averages. Entropy, or disorder, always increases on average. But when you shrink your engine down to a single particle, the law of averages gets fuzzy. The team observed moments where this microscopic engine seemed to defy the second law of thermodynamics. There were fleeting instants where it ran in reverse, taking in heat and cooling down, or performing work without a clear input. These aren't violations of physics. They are rare events predicted by fluctuation theorems. It essentially means that for very small systems, purely by chance, you can occasionally borrow order from the universe, provided you pay it back later. So why does this matter? Why go to all this trouble for a 5-micrometer ball of glass? The size is actually the critical innovation here. Previously, researchers at places like ETH Zurich have done amazing work with nanospheres, objects 1,000 times smaller. Nanospheres are small enough to be cooled down to their quantum ground state, behaving like waves. But the King's College team chose a microsphere, which is massive by comparison. 5 micrometers is the scale of biological machinery. This experiment bridges the gap between atomic physics and biology. Inside your cells right now, there are motor proteins called kinesin. These are literal biological machines that walk along molecular tracks, dragging cargo to keep you alive. They operate in a storm. They are constantly being bombarded by water molecules, a chaotic thermal noise that should make precise movement impossible. Yet, they work with incredible efficiency. By building a heat engine at this specific size and subjecting it to extreme noise, the equivalent of 13 million degrees, physicists can simulate that biological chaos. They can scale up the noise to understand how molecular motors harness random energy to do work. But the implications go even further, touching on the holy grail of modern physics, quantum gravity. We have a major problem in physics right now. We have quantum mechanics, which explains the very small, and general relativity, which explains gravity and the very large. They do not get along. We don't know if gravity is a quantum force. To test this, we need to see if a massive object can exist in a quantum superposition, being in two places at once, and then measure if its gravitational field is also in two places at once. Nanospheres are too light to generate measurable gravity. We need massive particles, like the 5-micrometer glass spheres used in this experiment. But massive particles are incredibly hard to control. By learning to drive this heavy sphere to 13 million degrees and control its motion with active feedback, Dr. Millen's team is developing the, quote, handling skills required for the next step, cooling such a massive object down to absolute zero to test the quantum nature of gravity. Furthermore, this technology opens doors for thermodynamic computing. As our silicon transistors get smaller, heat and thermal noise become the enemy. But this experiment proves we can build engines that run on noise. We could theoretically design computing architectures that recycle thermal noise into information, turning a problem into a fuel source. It also suggests new sensors. A particle hovering with such high energy is incredibly sensitive. If a wave of dark matter or a high-frequency gravitational wave passed through the chamber, it would nudge the sphere in a detectable way. In conclusion, the 13 million degree glass sphere is more than just a headline. It is a masterclass in control. We have reached a point in human history where we can isolate a speck of dust in a vacuum and command it to dance with the energy of a star, all while keeping it cool enough to touch. We are rewriting the rulebook of thermodynamics for the microscopic world, peering into the machinery of life and laying the groundwork to see if gravity itself is quantum. It is a reminder that in the quantum and microscopic realms, intuition is the first thing you have to leave at the door. Thank you for listening to G Fun Facts Online.